Cool. Hi, my name is Melvin.
And hello, my name is Stefan.
Okay, so our project is MNIST. Okay. Um, what type of problem do we have? Our problem is classification. We will use a CNN in order to classify numbers on the MNIST dataset. We will use two layers in order to classify these numbers within the MNIST dataset. Here's just an example of what a CNN does. It extracts features from image and within different layers shrinks that into an output that is understood by a trained model and outputs what it most likely thinks that image represents. Um, this is an example of a kernel that slides through an image. You can see the convolution here as it starts shrinking in size, and then it gets flattened into a layer and into an output. Yeah.
So the data set that we're going to use in order to implement uh this image classification is called the MNIST data set. It's a data set that originates from TensorFlow, in which it contains a total data set of about roughly 70,000 images of images ranging from 0 to 9. Each image is labeled, as you could see within um, the lower right, bottom right portion of the slide. It shows a some letter, I mean, some number, and each number is labeled with its corresponding value.
A numerical incentive is what we had. We wanted to see if we could apply this in any way. One of the more known or conventional applications is sorting mail. It's known that mail is very tricky to organize, and you can use a CNN to essentially scan the address and extract useful information. It is a little more on the difficult side because on an address you have numbers and letters. Therefore, it can be a little tricky to well, it's very tricky to distinguish uh, exactly what it is you're looking for on mail. It's also useful in identifying numbers on a license plate or in a like it's useful in a crime when a car is getting away. Sometimes you only catch glimpses and the image quality can be very poor. So CNN could definitely help you sort of predict or try to like figure out what it is that you're doing. And it also helps when automating checking, like when you deposit a check via your phone or any device, you might want to use a CNN to scan the numbers that are there. It's just really good way to automate like many things we don't really realize could be automated. And so yeah, we our goal is to try and create something that can sort of pick up on numbers and classify them. And yeah.
Okay, so now within our pre-processing stage, what we did was, in general, sorry, when in images, at least in images, normally you will look at the images through the pixel values, and these pixel values will be range from 0 to 255. However, within our models, which we'll soon present momentarily, these values will be extremely large, too large for the for the CNN to actually comprehend what what to comprehend what's the actual numbers being input, because it's getting a variety of different numbers. So rather than giving these huge array of numbers, we will normalize the function to 0 to 1, so that it will be easier for the so it would be less intense for the model to readjust its weights, or even just pass through certain information to the model. Additionally, we also resize the images to make sure that the images are all the same. had it not been the same, it would have caused issues, particularly when training the images. Because if you have an image that's, let's say, 28 by 28, and you have another image that's 32 by 32, the model will be very confused on how to handle those certain images. If you have a model that's only trained or at least structured to handle it in a 28 by 28 image, and it's now forced to take a 32 by 32 image, then the model wouldn't understand how to go about that. So in order to prevent that from occurring, we put the model, at least structure the model so that it can handle the same image, at least the same image size. Additionally, we also um after this, at least after doing these two steps, the normalization along with restructuring the dimensions, we also decided to calculate the mean and variance, which are results are shown in the bottom. With the mean pixel value of about 13%, it shows that a majority, that the about 13% of the image is considered a non-black image, at least I mean, not at least a non-black part of the image. So these 13% and also 9% from the variance basically is showing how is at least revealing that the overall image of itself is really just a black background, which is great because now the image is able to at least detect a very small segment of the part of the image that we really care about, which is the value itself, well, at least the numeric value itself. So even though even though that small numeric value, or at least the pixels associated with it, is a very minuscule number, it's fine because in this case, it shows that there's at least some pixel values being detected, and those pixel values are just a very small fragment of the overall image.
So, like Stefan was saying earlier, these are our first impressions. Notice that there are a lot of zero pixel values here. As you can see, it's not that easy to see here. Um, Most likely these images were inverted as we tend to write in black, but just for the sake of um, seeing and understanding these images, uh, we see here that we have pixel intensities that tend towards zero, and the numbers themselves are what increase the pixel intensity here. Um, the gray intensities here signify edges, which are really it's actually very helpful that we have the edges here in the pixel intensity because it makes it easier for us to sort of compare what numbers have what types of pixel intensities or tend to have similar pixel intensities when we actually run the um,
And additionally, along with that as well, we also decided to keep not only keep the same variance, but also find keep the principal component, utilize component analysis, or PCA for short, to show basically what the variance would look like after plotting on two dimensions. And basically, at least from the graph on the right hand side, it shows a cluster of the different types of digit values, which digit values appear the most, and at least appear the most based on this PCA scale.
okay. This is where we trained. Here you can see the different layers we have. We have a convolutional layer. We have pooling layers. This is our two layers for convolution. Um, this was just to shrink it more. Our dropout layer so we don't overfit. And this is where we flatten out to make our guess. We used here we used about 10 epochs. And here's our training accuracy. As you can see, our accuracy is actually pretty good when we trained.
along with that, because of the successes and relatively high accuracy from our training data, although I would like to say that because of the already high accuracy that was originally present, and even under the first epoch, which was 82%, and then after 3 or 4 epochs, it ended up staying in the 90s. It would eventually stagnate. So I would say that it would have just been fine if we just trained under maybe 5 or 6 epochs as opposed to 10. But besides that, even then, the accuracy was present during the testing in the testing set. So here below we see several numbers from the testing, at least the validation set. So you could kind of tell that even though there's some numbers that do appear more than once, such as let's say 9, you could also see that the 9 is also written in different ways, which is in some ways kind of reminiscent to how us humans would write, let's say, certain numbers or even letters slightly differently. How I might write, let's say, for example, the letter. I'm not. Pardon, apologies. Not the letter. Number 3, for instance, might be slightly different from how Melvin might write histories. Yet we are able to still understand that based on certain features and certain at least certain features and certain parts of the number, we're able to associate it with that certain number, or at least classify it correctly. This is the same case even in the validation set. So for instance, and also I like to keep this in mind that the first index in this validation set said 0, so bear with me. So when we decide to test from the index 7, which was this number here, well, we could tell it's 9. The convolutional neural network was able to classify it as 9 with a 100% confidence rate. Additionally, when testing it from index 3, the CNN model gave us another 100% accuracy, classifying it correctly as the number 0, which shows that due to the testing along with the substantial size of the training data, it greatly helped us figure out at least figure out how to correctly identify and classify these numbers correctly, even despite their slightly different handwritings.
Yeah, and I also like to add on that what we did earlier with the PCA actually seems to have like helped increase, or I don't say increase, but decrease, sorry, the time that it takes to train, as we actually shrink the dimensions of the image. It becomes easier for the model to essentially go through that entire data set and without losing much of the variance, have very good results. And so, yeah, here we go to a second round of training using K nearest neighbors. We essentially use a five-fold split, and these were our accuracies. More or less, we had a accuracy of 97, just pretty good actually. Um, Not much of a difference from the old training that the first training that we did, but yeah, it's pretty good. Go here. Stefan can explain
And
more.
additionally, along with the k-nearest neighbor, we also use a support vector machine, which or to use an accuracy about 98%, which is also roughly on par with the k-nearest neighbor and the convolutional neural network accuracies. Here we basically, it's in a nutshell, the support vector machine is used to show which classes are correct and which classes are incorrect, particularly when comparing between the true ground images along with the predicted ground images. And basically it just shows how and basically it shows how accurate not only how accurate the classes were, but also which parts of the classes, at least which part of the classes made errors, or at least made errors. However, at least based on the graph, at least particularly the the graph on on the bottom right, where we're able to at least see that for the most part, even though there are some slight um class mistakes, for the most part, the true ground image is pretty much aligned with the predicted images, which shows that even despite slight class like class class diff a very slight incorrect classes are being predicted. For the most part, the model itself is relatively accurate.
Okay, some trials and errors. We originally started off with very ambitious, wanted to make a mail sorting algorithm slash program that would have required us to go through extensive research. Uh, Here, as you can see, we try to classify numbers inside of specific bounding box. It ended up picking up the writing. This was us trying to decipher this number over here. Um, when shrinking the size of the bounding box, we saw that it was also not very good at picking where the actual numbers were. And that would be another entire thing of trying to distinguish how we could essentially outline numbers or distinguish them when the handwriting itself was already pretty bad. Um, and so we decided to go back and sort of rethink what it was we wanted our project to be. Definitely, if we had more time, we could definitely try and figure out how to implement this, build a better pipeline. But yeah, those were some tribulations we had. These are references. Just IBM is really helpful. TensorFlow is also really helpful. Really good documentation. And sklearn had a great library for k-nearest neighbors, but also the stats and everything else.
And here is basically our general code base that we use for both for not both, but for the convolutional neural network, the k-nearest neighbor algorithm, and our not supreme, support vector machine. So here we basically show the libraries that we use. So TensorFlow, just so we could get at least access some of the um, built-in models, such as the convolutional neural network, which also saved us a lot of time when running when not only creating the model but also even doing the training and the testing. We also use pandas, matplotlib, numpy, matplotlib especially, so we could saw a lot of the graphs that you were able to see previously, especially especially the error progress charts came from matplotlib. We also use Keras and also a sequential model, particularly, which is more useful for the convolutional neural networks, along with using sklearn, which basically provided us with some of the built-in functions that were much more used for constructing the k-nearest neighbor algorithm, along with the support vector machine as well.
Yeah, and our appendix basically goes through how to essentially from scratch do what we did, calculating the mean, showing all of the charts that we made. Here is the visualization of the actual. Uh, it's actually this one over here. I can show you. It's this. It's showing how the PCA actually changes the dimensions of our data set and how leaves the variance, but definitely makes it easier for our our computer to train. Um, yeah, here's the layers. We use the ReLU activation. Um, here's the initial input, the 28 by 28 image, and we add the one to make it three dimensions because our um, our model itself thinks in three dimensions. And this was just to show that it was like a grayscale image since there's only one dimension. If it was a color image, it would have been three different channels. But since we only have one channel, it's a one. Um, these are our layers. Again, our second layer, more layers. This was for the dropout, flattening, and here's our optimizer for gradient descent. Yeah, it's just a bunch of stuff that we use to sort of get the job done here. This is our SVM implementation, and yeah, that was that was basically it. It was definitely an interesting research project. Well, with the time we had, definitely would have been easier if we had more members. Um, and
Definitely.
yeah, I'm pretty happy with the results that we got. Um, Yeah, that will be it. That's all from us. Any questions? Any statements from you, Stefan?
No, I think that
Concludes
I
our
think you mainly said most of the bulk of it. I believe that given our
circumstance.
time and our time, given the time and resources that we had, I think we used both of those things to the best of our advantage. I believe that this project came out better than originally expected. And I believe that not only will, even though this was a small project, a small project, but I think that certain aspects of it could be implemented. And you mentioned this earlier on in the in the um, in the presentation that if let's say we're able to do classification on just regular images of numbers, then we could potentially do it on real world applications. Like let's say like with mail, or at least trying to sort mail based on zip codes or addresses and things like that. Maybe this could also be used for plates or plate identification or things, let's say, that could be used in financial systems, like trying to detect fraud or trying to approve certain loans or things that are related to that. And even then, not only just with numbers, but even with characters too. If we could detect certain aspects of how numbers are created, I believe we can also create certain aspects of how characters are related, or at least are related to, despite the differences in handwriting. So although I do believe that this is a small, although it's a relatively small project, I do believe that the results and results from this could show that this could be applied in many other real world applications and real world applications and even in other areas of machine learning as well.
Yeah. Mm. All right, that's it for all of us. Thank you so much, and
Thank you very
yeah,
much.